Welcome to the Explainer. Welcome to the Explainer. So, have you ever looked at the periodic table of elements and felt like, well, you were just staring at this chaotic jumble of letters and numbers? Yeah, you are definitely not alone. But today, we're going to completely transform how you see it. We're turning that seemingly random chart into a highly predictable cheat sheet of the universe. By the time we wrap up, you won't just be memorizing facts. No way. You'll actually be reading the underlying map of how matter is constructed. Okay, let's dive into our roadmap for today. We'll be covering 1. The periodic law explained. 2. Focus on atomic size. 3. The subatomic tug of war. 4. Reading the periodic map. And finally, number 5, we're going to test your knowledge. Let's get right into it. Section 1. The periodic law explained. Order out of chaos. Okay, so it's absolutely crucial to understand right from the get-go that the elements aren't just randomly thrown together on a grid. There's a deep foundational rule governing exactly where everything sits, and that's the periodic law. It tells us that the physical and chemical properties of elements are the periodic function of their atomic numbers. Now, what does that actually mean in plain English? Basically, it means that as you increase the atomic number, as you count up through the elements, their properties actually recur at regular, predictable intervals. Think of it like the days of the week or the seasons of the year. There's a repeating pattern setting the stage for everything. Now, what's really interesting about this slide is the definition of a periodic property. It's the actual change or the periodic variation in those properties as the atomic number goes up. And this is a total game changer because it proves the periodic table isn't just some storage cabinet for elements. It's actually a dynamic map of physical changes. If you know how to read these properties, you can predict exactly how an element is going to behave just based on its zip code on the table. Section 2. Focus on atomic size. Narrowing it down. Because the table organizes so much information, we really need to focus our lens today. There are 4 main periodic properties that change as you move around the table: atomic radius or size, ionization energy, electron affinity, and electronegativity. Now, all of these are super important, but for this explainer, we're going to direct our full attention to just the very first one, atomic radius or atomic size. Because honestly, by mastering this single physical property, the rest of the table's secrets really begin to unlock. So, what exactly are we measuring here? Atomic size, or atomic radius, is basically the physical footprint of the atom. It's the measure of the distance from the central nucleus all the way out to the outermost electronic shell. Or look at it this way: if you have 2 of the closest identical atoms side by side, it's half the distance between their 2 nuclei. Either way you slice it, we're just trying to find the absolute outer edge of the atom to see exactly how much physical space it takes up. And when we measure that physical footprint, we use a unit called the picometer. I want to highlight this because it's just mind-blowing to think about the scale we're dealing with. A picometer is literally 1 trillionth of a meter. These atoms are incredibly tiny, yet it's the precise differences in these picometer measurements that dictate the shape and function of, well, the whole shebang. Everything in our universe. Section 3. The subatomic tug of war. The forces within. To understand why one atom is bigger or smaller than another, we have to zoom deep inside the atom itself and look at the invisible forces battling it out. An atom's final size isn't random at all. It depends on 3 things. 1. Effective nuclear charge.
2. Shielding or screening effect. And 3. The principal quantum number. Now, I know these sound like super complex textbook terms, but don't worry, we're going to decode exactly what each of these means right now.
It all starts with nuclear attraction. Deep in the center of the atom, the nucleus is packed with positive protons, and they are pulling on the negative electrons in the outermost shell. So the crucial point here is that this is an inward pulling force. The higher the nuclear attraction, the tighter it pulls those electrons in. And what happens? You get a smaller atomic size. Conversely, lower attraction means a looser grip, making the atom bigger.
Okay, here is the ultimate subatomic tug of war. On one side, you have the effective nuclear charge. This is the net positive charge that the outermost electron actually feels. It's the muscle pulling the atom inward. But fighting against it is the shielding or screening effect. This is the outward block. The inner core electrons literally get in the way and block some of that nuclear attraction, shielding those outer electrons. So it's simple. If the effective nuclear charge wins, the atom shrinks. If the shielding effect wins, the atom expands. The third and final factor is the principal quantum number, which is really just a fancy scientific way of saying the number of electron shells the atom has. Think of it exactly like adding layers to an onion. The higher the principal quantum number, the more shells the atom has. And obviously, more shells mean a bigger atomic size. A lower number means fewer shells and a smaller atom. It really is that straightforward. Section 4. Reading the periodic map. Trends across the table. Let's move to the table and see how this builds. Now that we've got the internal roles down, the pulling, the shielding, the shells, we can map them out onto the periodic table to see the big picture. Let's look at the two main directions. If we move across a period from left to right, we get increased nuclear attraction. So the final size outcome is that the atom decreases in size. But if we move down a group from top to bottom, the cause is an increased principal quantum number and shielding. So the size actually increases. Let's break down the why for each of these. When you read the table from left to right across the period, the atomic number goes up, meaning we're adding more positive protons to the nucleus. Because of that, the effective nuclear charge increases. But here's the kicker. The screening effect and the number of shells stay pretty much constant. So the inward pull gets stronger, but the outward block stays exactly the same. The nucleus just pulls those outer electrons closer and closer. The result is a tighter pull, causing the atomic size to shrink from left to right. Now moving from top to bottom down a group. As you go down, the principal quantum number increases, meaning you're adding entirely new layers, new shells of electrons. And this brilliantly illustrates our tug of war. With all those new inner layers, the screening effect dramatically increases too, which blocks that nuclear attraction from reaching the outer edges. Moving down a column adds so many new shells and so much outward shielding that the outward push absolutely wins. The atom is literally forced to expand. Section 5. Test your knowledge. Active recall. Okay, let's turn you from a passive listener into an active participant. We're going to apply the exact logic we just covered to a quick challenge. Here's the first one. Arrange the following elements in increasing order of atomic size: oxygen, nitrogen, boron, and beryllium. Let's think through the map. These elements are in the same period, moving left to right. Recall our rule. Size decreases across the period from left to right because of that tighter nuclear pull. So if we want increasing order, smallest to largest, we actually have to start with the element furthest to the right, which is oxygen. Moving left, we get nitrogen, then boron, and finally the largest one on the far left, beryllium. So ONBB. Make sense? Let's try the second part of the quiz. Arrange these elements in increasing order of atomic size: beryllium, magnesium, calcium, and barium. Think about the trend. Here we are moving down a group, from top to bottom. Remember what happens there? We add shells, so the size increases. So the smallest is at the top, and the biggest is at the bottom. The increasing order is simply their order going down the table: beryllium, magnesium, calcium, and barium. If you got that, you are officially reading the map like a pro.
And that brings us to the end of our explainer. Just look at how far we've come. We went from a confusing grid of letters to a clear, predictive map governed by a subatomic tug of war. Mastering atomic size is huge. It unlocks the secret predictive power of chemical reactions across the entire universe. When you know an atom's size, you know its boundaries, its strengths, and exactly how it's going to interact with everything around it. So think about this. If a single measurement can decode the behavior of every known element,